different formula, different formulae of statistics, and after that we will calculate the overall properties or the overall properties of the matter starting from microscopic level, that is in the quantized energy level, that is applicable for atoms, molecules, etc., and its macroscopic or bulk properties. So that means here we will so derive provide a link between microscopic perspective of matter, that is in the quantized energy level of atomic or molecular levels, and its macroscopic or bulk properties what we have studied in the general thermodynamics part. So this approach can be used to calculate the bulk thermodynamic properties such as internal energy, enthalpy, entropy, Gibbs energy of the system from structural and spectroscopic data of the microscopic species containing thermodynamic system. So that means generally if we take any characterization of a system from the characterization techniques or from the different spectroscopic technique, we will calculate the different values of internal energy, the enthalpy, entropy, or Gibbs energy from atomic or molecular level. That means from the microscopic level. And after that, we will use these values from the microscopic level to calculate the bulk thermodynamic properties of the said material. And in a way, statistical thermodynamics can be considered as a mathematical tool that bridges the gap between the properties of individual atoms or molecules in a system and that of microscopic thermodynamic property of a bulk matter. So in the general thermodynamics, we have discussed about the macroscopic thermodynamic properties of the bulk matter. In the general thermodynamics, we are not considering the properties of the matter from atomic or molecular level. So are there in the general thermodynamic part, we have considered the properties of the matter from bulk level. And in the statistical thermodynamics, we will use some mathematical tools or will use statistics to calculate the shared properties of the matter from the individual atomic or molecular levels, and after that we will summarize we will take the summary of the summation of the property to calculate the overall property of the bulk matter. Alternatively, statistical thermodynamics can be visualized as a vehicle that serves to provide a means to extend the properties of the individual atoms or molecules to a large collection of them. So before going to the details of the statistical thermodynamics, first we will discuss some statistical or simple mathematical techniques. So here, the classical thermodynamics used the data based upon the bulk properties of the matter. In the statistical thermodynamics, we have so used the different data to know the bulk properties of the matter like density, pressure, heat capacity, etc. Where the statistical thermodynamics use the molecular properties like bond length, quantized energy level, vibrational frequencies, etc. For example, if we consider the enthalpy of formation of water molecule, here the enthalpy of formation of water molecule is minus 241.8 kilojoule per mole at room temperature and 1 atmospheric pressure. It is so that means that the enthalpy change associated with formation of 1 mole of water vapor from its constituent element in the standard state under standard condition. So here in this example, it is given that enthalpy of formation of water. So enthalpy of formation of water is minus 241.8 kilojoule per mole. That means minus 241.8 kilojoule per kilojoule amount of energy will be released when 1 mole of water vapor will be formed from their constituent elements oxygen and hydrogen. And classically speaking, it has nothing to do with the microscopic nature of the species. So if you tell the enthalpy of formation of water, that is minus 241.8 kilojoule per mole, that means that if you classically tell that So it has nothing to do with the microscopic nature of the species involved and what determines the observed value. On the other hand, statistical thermodynamics deals with what the individual atom and molecule determine the observed value. That means using the statistical thermodynamic, we will calculate or will find the result from atomic or molecular level. That means from the quantum level. So the statistical thermodynamics ignores molecular complexity and quantum. So in the statistical thermodynamics, we are not discussed about the structure of the molecule and what are the different atoms present and what are the different structure of the molecule at different conditions. But in the statistical thermodynamics, all these things we should consider. That is, the quantum mechanical nature of the molecules are not considered in general thermodynamics or classical thermodynamics. Whereas in statistical thermodynamics, that will completely deals with the quantum mechanical nature of the atoms and molecules. Whenever we will consider the nature of any microscopic particle, so in that case we must consider the quantum mechanics so related to the atoms or molecules. And here the statistical thermodynamics to represent a probable approach to study the thermodynamic systems. Therefore, basic understanding of the probability and the related concept that must be so required to know the details about the statistical thermodynamics. So first we'll discuss the basic probability theory. In the basic probability theory, here we will take an experiment. If an experiment can have more than one outcome, then the probability refers to change in getting a particular outcome. Suppose we will perform any type of experiment in the laboratory, and if the experiment and if there is a chance to get more than one outcome, then the most common example using the probability, suppose you will take the example of tossing a coil. So if you toss a coil, so we know that a coil has two faces, that is head and tail, and the experiment has and if the experiment is tossing the coil, so it has two probable outcomes, either head or tail. So head and tail are so referred to the probable events or probable outcomes for tossing a coil, and the probability of getting a particular result, so that is 1 by 2, mathematically so written as the probability of getting head, that is 1 by 2. And similarly, so there is 50% chance to getting a head and 50% chance to getting a tail. So that is the probability to getting the head is 1 by 2 or 0.5, and similarly the probability to getting the tail is 0.5. And if we add the total probability of the event or the total probability of the results in an experiment, that is always equals to 1. Maybe the experiment have the different possible so results, but if we add the total probability of the different possible so results, so that will become 1. So if two coins are tossed simultaneously, again we will move to another example where two coins are tossed simultaneously, then the possible outcomes may be so in the table it is given that so this is the first coin and this is the second coin. So the possible outcome may be head head, head tail, tail head, and tail tail. And here we will find four different possible results are there. So the collection of all possible outcomes in an experiment, so that is known as sample space. An event so refers to any outcome or collection of outcomes of the sample space, or may be included in the null set as well as a set as possible outcome. For example, the sample space for tossing two coins, so so the probable outcome or the probable so results in statistics are called sample space. So if you toss two coins, the sample space, if you toss two coins, the sample space are head head, head head, tail tail, head tail, and tail head. So there are four different sample space are there for tossing two coins simultaneously. These, these constitute the sample space for the experiment. And now coming to next experiment, next example. Now, so let us consider an example traveling from a city A to city B via city, traveling from city A to city C via city B. So that means in the intermediate position, you will find city B. If there are X ways of reaching city B from city A and Y ways to reaching from city B to city C. So here your initial city is A and final city is C, and the intermediate city is B. Suppose there are X ways for reaching A to B and Y ways from B to C, then the total number of ways you can move from A to C will be X into Y. Therefore, the sample space for the event going from city A to C will be X into Y element. You may be note that in the probability an event may contain a series of actions, so the sample space contains all possible outcomes. So sample space means that should contains all possible, so results are all possible outcomes. Now coming to, if there are, if the sample space is, if the total possible outcomes, or that is called sample space, is n, if the sample space has n mutually exclusive event and an event of interest A occurs I times, then the probability of that event is given as PA, that is I divided by N. Again coming to that, if the sample space has n mutually exclusive events and an event of interest A occurs I times, so that means from n number of event, the particular event I occurs A times, then the probability for getting the result A is I divided by N. Therefore, the probability to getting one head and one tail is 2 divided by 4, that is 1 by 2. And similarly, the probability to getting two heads is 1 by 4, that is 0.25. The probability to getting two tails is 1 by 4, that is 0.25, and the probability to getting one head and one tail, that is 2 by 4. So the result is 0.5, and if you add all the probabilities, so that will give rise to 1. So here we will discuss one example. Consider an experiment involving tossing a coin 4 times. That means you have to toss the coin for 4 times and calculate the probability of getting at least 2 heads in the experiment. So here in this in the table it is given. So you have to toss a coin for 4 times, and here, and you have to calculate the probability to getting at least 2 heads. So in this case, we have a coin that is to be tossed for 4 times, and in every toss we have 2 possible outcomes, either head or tail. We can write down all the possible outcomes in this experiment as follows. Suppose this is outcome experiment number 1. First toss head, second toss head, third head, and fourth head. So this is one outcome. And similarly, there are 16 different outcomes are possible. So out of the 16 different outcomes, we have to find out the probability to getting at least 2 heads. So at least 2 head means 2 times head or 3 times head or 4 times head. So thus there are a total 16 possible outcomes of the experiment. Out of experiment of tossing a coin for 4 times, the sample space has 16 outcomes. Out of the 16 possible outcomes, 11 outcomes are as per our requirement of having at least two heads. So the probability to getting at least two heads is 11 divided by 16. And similarly, when you roll an unloaded dice, we know that dice it has six faces, right? So the one which the chance of any one of the six faces to be on the top face is the same that is any for other faces. The probability that we will get a number 6 on the top face is 1 by 6. So if you roll a dice to the total number of possible events should be 6, and the probability to getting 6 on the top face, that is 1 by 6, and it is one of the 6 possible outcomes. Similarly, the probability to getting other numbers from 1 to 5 on the top face will be 1 by 6 plus 1 by 6 plus 1 by 6 5 times, and hence if you add the total probability, so that will become 1. Now consider a slightly more complex case, that is rolling a pair of dice. So the people so roll a pair of dice, and from the pair of dice there is only one outcome in which get the sum of the numbers on the top face equals to 2, and also sum of the numbers on the top face equals to 12. So that is only one possible is there. So outcome 2, number of ways 1, and the total outcome will be 12, number of ways 1. The total outcome will be 3, the number of ways 2, so that is 1 1 2 or 2 1. And similarly the outcome should be 4, and here the number of ways 3. So the sample space for rolling a pair of dice has total 36 outcomes, and from these 36 outcomes, throwing a 7 is most probable event. So that means here we are rolling two dice simultaneously, and what is the probability to getting a total number of 7 on the top? So it has the maximum probability. So throwing a 7 is the most probable, that is one can be accomplished with the greatest number of ways. So it can occur 6 possible ways. So 6 possible ways we can get a total 7 on the top face. So the 6 possible ways are: for the first dice it is 1, for the second it is 6. Similarly for the first dice 2, for second 5, for the first 3, for second 4, for the first 4, the second 3, first 5, second 2, first 6, second 1. So these are the 6 possible ways we can get 7, we can get the total number 7. And these have been, and if you consider so what are the possible ways to get the total number 2? So that is one possible way, only one possible way to get the total number 2. And similarly only one possible way to get the total number 12 out of the 36 possible results. And if we consider the outcome should be 7, the possible ways are 6. Here so we have discussed that one. It is important to state that the random or randomized variables or the quantities, those variables whose value can change without the course of experiment or series of events. In the above experiment, the sides of the coin, the number of the top face of the dice are varied that change the outcome of the experiment. The variable can be discrete values, that is the ones that can have countable number of values. For example, if you consider a coin has only two sides, and if it has only two variables, where the dice has 6 variables. So in the example of coins, it has two sides, so it has two variables. But when we will consider a dice, it has six sides and hence six variables are there. In the event of picking one student from out of the 60 students, so if you want to take one student out of the 60 student in a class, so it has 60 variables. So it is important to note that the number of outcome may be astronomical. However, as long as the possible outcomes are countable, it will remain discrete. In case of discrete variables, the sample space is represented as a collection of all the variables. For example, sample space in the experiment involving throwing of the dice will be, it may be, so if you throw a single dice, the sample space may be 1, 2, 3, 4, 5, 6. So these are the sample space. On the other hand, we can have continuous variables that can have any value in the given range of values. Say the real number, if you consider, if you say a real number between 0 to 1, it has example of continuous variables, and that means it has no discrete value. So if discrete values will be there, so the discrete values can be calculated from the whole number. But if we take any fraction number, so that will be a continuous variable. Contrasting with the discrete variables, a continuous variable has uncountable set of possible outcomes. So for discrete variable has a countable set of possible outcomes. But if you consider continuous variable, it has uncountable set of possible outcomes or uncountable set of possible result. Temperature is another example of continuous variables, as the system temperature can have anywhere from 0 Kelvin onwards. And so we can take, so if you consider temperature, it can have any values from 0 Kelvin onwards, and hence it is one type of continuous variable. And if you consider another example, that could be distance traveled by different peoples within a given time interval, so this is one type of continuous variable. So in the continuous variable, there can be infinite number of possible results or uncountable number of set of possible results. But for discrete variable, so that is countable number of possible results. In case of continuous variable, the sample space is represented by starting a set of limits which the variables vary. That means if you consider any type of continuous variable, the variable x may have the value in the range, that is x is greater than equals to a and less than equals to b. That means the values of x can be uh, the value of x has an range from a to b. You can take any value. So this type of representation can be given for continuous variable. For example, if the continuous variable x can have any values from 1 to 100, it can be represented as x greater than equals to 1, less than equals to 0. So less than equals to 100. Now it is persistent to point out the chemical systems that we are interested. So that is the observables are random and fluctuating in nature. For example, the instantaneous vapor pressure of a liquid in equilibrium with its vapor continuously fluctuate around different values. So it has continuous values, and similarly the energy of a system at constant temperature or the value of the system at a constant pressure keep on fluctuating around the average values. However, the outcome of the measurement may be different, but the average value cannot be predicted. Therefore, we need to some kind of probability distribution to describe the behavior of the random variables. So here in the statistical thermodynamics, we will find out a probability distribution where random variables will be there or continuous variables will be there. But for discrete variables, so there is a possible to get a discrete result or particular result. Now coming to, so first we will discuss about the basic things of permutation and combination. So to calculate the probability of an event, we need to count the total number of events. So if we want to find the probability of a particular result out of the total result, in that case we have to use permutation and combination. So this is an easy exercise in when small number of events are there. However, in chemistry we are dealing with 1 mole. 1 mole means 6.02 into 10 to the power 23 numbers. So if you take 1 mole of atom, that means 6.022 into 10 to the power 23, or Avogadro's number of atoms. So in chemistry, as we are dealing with large numbers, the exercise becomes difficult when the number of events will be very large. Say, for example, if you tossing 100 coins or rolling 20 dice, a much easier way to calculate the total number of outcome of an experiment will be based upon the fundamental counting principle. In that example, we have taken two coins or two dice. So the from the two coins, the total possible number of two heads, or from two dice, the possible number of getting the result seven can be counted. But if 100 coins or 20 dice will be there, so it will be very difficult to count the total possible to get a particular event, and hence for that we have to use fundamental counting principle. Now according to this principle, if there are n1 ways of doing first thing, n2 ways of doing second thing, and n3 ways of doing third thing, and so on, then the total number of possible outcome is n1 into n2 into n3, and so on. Now let us calculate the total number of outcome for rolling a pair of dice by using fundamental counting principle. So this is the fundamental counting principle, and if you apply the fundamental counting principle for rolling of a pair of dice, what we have solved there. Here we will apply the fundamental counting principle. For rolling of first dice, there are 6 possible outcomes. Similarly, for rolling of second dice, there are also 6 possible outcomes. Now, according to the fundamental counting principle, the total number of outcomes for rolling of two dice will be 6 into 6, 36. And similarly, the total number of outcomes for rolling of three dice is 6 into 6 into 6, that is 216. And similarly, if we will consider the total number of outcomes for rolling of n number of dice, the total number of outcomes will be 6 to the power n. It is equivalent to the number of outcomes for drawing R object, that of a total number of n object. It is equivalent to the number of outcomes for drawing R object from a total number of n object, such that firstly the object are replaced after every pick, and secondly the order in which the objects are drawn does not matter, and giving the expression, and hence for this the number of permutations equals to n to the power r. For example, if we'll so here this principle we can take one example. For example, for tossing of two coins, we have considered certain events where head, tail, and tail head are equivalent. So if we will take equivalent head, tail, and tail head will be equivalent, then the order for choosing variable and objects does not affect the total outcomes. Now we'll discuss the permutations. Let us now count the total number of outcomes when the order for choosing the object does not affect the total number of possible outcomes with the help of the example. So here we will discuss the example. So by discussing these examples, we can easily understood the theories behind this. Now consider a box containing 4 different balls A, B, C, and D. Now calculate the number of possible ways for randomly selecting 4 original balls out of the box without any replacement. We have to calculate the number of possible ways for randomly selecting 4 original balls out of the box without any replacement. Now the first ball The first ball chosen can have any four availables, and for the second pick, it has remaining three balls. For the third ball to be chosen, it has two remaining balls. So for choosing the first ball, it has four possibilities. For second ball, it has three possibilities. For choosing the third ball, it has two possibilities, and for choosing the last ball, only one possibility will be there. Hence, the number of ways for four sequential but independent choice can be 4 into 3 into 2 into 1, that is 24. That means 24 different ways you can choose four different balls. That means you can choose initially ball A or ball B or ball C or ball D. So four possible ways are there. And for second ball, from the first chance or to pick the first ball, it has four possibilities. You can take A or B or C or D. So after choosing the first ball, if you want to choose the second ball, it has three possibilities. And similarly, after choosing the first and second ball, if you want to choose the third ball, it has two possibilities. And after choosing first, second, and third ball, if you want to choose the fourth ball, it has only one possibility, and hence the total number of independent possibilities will be 4 into 3 into 2 into 1, that is 24. So these 24 possible ways of randomly selecting four original balls are the number of possible arrangements or permutations of any single sequence of the four balls, that is A, B, C, D. You may note that if the balls are not labeled, there are that means if the balls are not labeled as A, B, C, or D, there were indistinguishable 24 possible arrangements discussed above would refer to only one combination. That is, only one single collection or combination of the four balls will be exist. And also, if you choose to disregard the ordering of the picking of the balls, then the event of the balls are labeled, then we will have only one combination. That means if the balls are indistinguishable, that means if the balls are not labeled as A, B, C, D, that means you can choose any ball. So it has only one combination. You can choose A or B or C because all the four balls are not labeled. So it has only one combination. Now coming to one example, calculate the number of possible unique 9-digit numbers that can be formed by using digits 1 to 9, just one in the number. So while writing the desired number, there are 9 choices available for the first digit, and for the second digit we have 8 choice. That means no repetition will be there. You have to write a 9-digit number from 1 to 9, and no repetition of the number will be allowed. Then for writing the first digit, you have 9 possibilities. For writing the second digit, you have 8 possibilities. For writing the third digit, you have 7 possibilities. And similar way, the total number of possible unique 9-digit number will be 9 into 8 into 7, so that is 9 factorial. Each number given in the example 3.3 made up to unique arrangement of the number, so that is known as permutation of 9 numerals. Thus, from this example, we say that permutation is a unique arrangement of all the available objects in which the order of selection affects the arrangement. In, in such type of permutation, all available objects are used in the arrangement. The number of permutations are for drawing n objects from a set of n objects can be without any replacement can be equal to n factorial, and the number of permutation can be written as pn, or that is and the result is n factorial. Let us take another example. How many 5-letter codes of English alphabet can be written in which no letter can be repeated? We know that there are 26 English alphabets are there, we have to write a 5-letter code without repeating any letter. So the first place for the required code can have 26 options, and for the second place it has 25 options. For the third place it has 24 options, because already two letters are chosen. And similarly for the third place it has 23 options. For the for the fifth place it has 22 options. And to write unique 5-letter codes without repeating any letter, we have 26 into 25 into 24 into 23 into 22 number of possibilities are there. So in this particular example 3.4, that represent the types of formula, the types of permutation of object, in which out of all the object n equals to 26 and only a subset r equals to 5 is used in the arrangement. So that means total number of possible objects are 26. Out of the total number of possible objects, we have to choose 5 objects, and hence the expression for obtained in this example can be written in terms of n and r. And here the formula for the permutation p equals to n into n minus 1 into n minus 2 into n minus 3 up to n minus r plus 1. So there are general expression for the possible number of permutations of R object out of a set of n object can be written as NPR or permutation NR, and the value of NPR will be equals to n whole into n minus 1 into n minus 2 into n minus 3 up to dot dot n minus r plus 1 into n minus r into n minus r minus 1 up to dot dot 3 to 1 divided by n minus r factorial. So this equation becomes, so the numerator of this equation becomes n factorial. So thus the total number of permutation for choosing r object out of the total of n object without any repetition may be written as npr, that is equals to n factorial divided by n minus r factorial. So in this section, we know that if there are total number of n objects and the possible ways to choose r objects without any type of repetition, and the result will be n factorial divided by n minus r factorial, where r where n is less than equals to r, which is less than 0. This refers to the number of permutations of n object taken r at a time. And you may note that when r equals to n, then the denominator will become 0, and 0 factorial is 1. Therefore, the number of permutation will be only n factorial. So if you take total number of the number of ways to choose total n number of object is n factorial, and the number of ways to choose n number of r number of object from total n number of object will be n factorial divided by n minus r factorial without any type of repetition. Now the question will come, if repetition of the object is allowed. So all of you understood up to this?
Yes, sir.
Okay. So up to this we have discussed if no repetition will be allowed. Now the question is that if repetition of the object is allowed for every object to be chosen from the n object, so that may be total number of objects are n, we have to choose r object where repetition of object is allowed. Then thus the number of permutations for taking r object from total number of n object with repetition will be n to the power r. When repetition will be not there, the number of possible ways is n factorial divided by n minus r factorial. But if repetition will be there, the result will be n to the power r. And similarly, the number of permutations of n object where R1 objects are one kind, R2 objects are second kind, and Rk objects are kth kind, and the expression can be written as n factorial divided by R1 factorial into R2 factorial into R3 factorial up to dot dot Rk factorial. So these are the different ways of choosing n r number of objects from total n number of objects with repetition, without repetition, etc. Now coming to configuration. Now up to this we have not considered the configuration. That means while we are discussing the tossing of two coins and the result to get one head and one tail is HT or TH. There are two possible ways. But in this case, we have not considered the configuration. So there are certain conditions in which order of choosing the object is not important. For example, if we want to select two books out of the three available books, suppose three books are available A, B, C, and you want to choose two books out of A, B, C, and here the possible results are either you can choose A, B, or A, C, or B, C. In this case, whether you choose A first, then B, or choose B first, then A, you will get same set of books. So that means here we are not considering the configuration. Therefore, the order of choosing the object does not affect the result. But if you have three different, and here if you not consider the configuration, you have three different combinations of two books out of the three books. So there are three books, and if you want to choose two books out of the three books, you have three possible combinations are there: A B, A C, and B C. But when the order of arranging the object is not important, so here order of arranging the here the first book is A and the second book is B, and there is another possibility is there, the first book is B and second book is A. So if you will not consider the order of arrangement, or if you will not consider the configuration of choosing the books, then there will be three different ways for choosing two books out of three books. But when the order of arranging the object is considered, then the collection of R object out of the n object is known as combination or configuration. Therefore, configuration is an on-order arrangement of R object out of n object. The key difference between a permutation and a combination is that the so if configuration is not there, then the result will be from the permutation. But if you have to select a particular configuration, then combination term will be arise. So the key difference between a permutation and a combination is that the order of the element in a combination, it does not matter, it just where it does so in case of permutation. In simple word, there are no first place, second place, and so on in case of combination. But so for combination, there will be no first, second, or third place. So the combination of PQRS or PRSQ are identical, are not counted twice. While in case of permutations, the alphabet PQRS, the order of arranging PQRS are considered. Therefore, the number of combination represent all the different subsets contain R items that can be sampled from n distinct objects. Here, the specific arrangement of R object within the subset is irrelevant, and the number of combinations that can be obtained by dividing the number of permutations by the number of permutation are distinct object. So that is the number of combinations equals to number of permutations of R objects selected out of the total n number of objects divided by number of permutations and selected. So mathematically, the number of combinations equals to NPR divided by R factorial, and substituting NPR we get NCR. So that is the combination NCR equals to NPR divided by R factorial. That is N, and we know that NPR is N factorial divided by N minus R factorial. So the combination in the so if you get the combination NCR, that is equals to N factorial divided by R factorial into N minus R factorial. So we will consider one example here. Calculate the number of permutations and combinations possible while selecting 3 balls out of the 5 different balls taken in a box. So here the total number of balls n equals to 5, and you have to select 3 balls out of the 5 balls, and the permutation is 5p3. So that is equals to the number of permutations equals to 5p3, that is equals to 5 factorial divided by 5 minus 3 factorial, that is 5 factorial by 2 factorial, that is 60. And total number of configurations, that is equals to 5c3, that is 5 factorial divided by 3 factorial into 5 minus 3 factorial, that is 10. So the number of permutation is 60, where if you will consider the configurations are just 10. So this implies that for each configuration there can be more than one permutation possible. And the expression for number of possible outcomes for picking R object out of total n object under different conditions is discussed in this example, so that is given in this table. So the expression for number of possible outcomes for picking R object out of total n object under different conditions. So first one is, if replacement is not there but order is maintained, then you can use NPR, that is n factorial divided by n minus R factorial. If replacement is not there and order is not there, so the number of possibility will be decreased. Then you can choose NCR, that is n factorial divided by R factorial divided R factorial into n minus R factorial. If replacement is there and order, you have to maintain the order, so the number of possibilities is n to the power R. If replacement is there but no order, then the number of possibilities is n minus R minus 1 factorial divided by R factorial into n minus 1 factorial. So we have so far considered the situation or picking up a certain number of objects out of a given total number of conditions. Now let us take example. So we will discuss particular example for distributing object with or without restriction. Now let us take 3 identical boxes and consider the distribution of a red color ball among them. So 3 identical boxes are there. We have to arrange one red color ball within the any one of the 3 boxes. So let us take 3 identical boxes and consider the distribution of a red color ball among them. We know that it can be accomplished 3 different ways. So there will be 3 different ways of putting one red color ball within 3 identical boxes. So you can put the ball on first box one way, and similarly we can put the box on the second box another way. You can put the ball on the third box. So these are the 3 different ways. And we know that so now if you take 2 identical red balls, the balls are indistinguishable. 2 identical red balls, and here the balls are indistinguishable. And try to distribute them into 3 identical boxes, and condition that each box can have only one ball. So these are the 3 different possibles. So here also 3 different possibles to arrange 2 identical balls in 3 boxes. So this figure represent the possible ways for distributing one ball or distributing 2 identical balls among 3 identical boxes. Now coming to the next one, if we take the 2 balls which are distinguishable, that means one ball is red color and the other ball is blue color, right? And distribute among the three boxes, we have six possibilities. In this case, we have two indistinguishable balls. That means two identical balls, two red color balls. We have to arrange two same red color balls in three boxes, and the total number of possible ways is three. And if we arrange two distinguishable balls, that means one is red color and other one is blue color, in three identical boxes, then six possible ways are there. How six possible ways are there? So you can put the red box, so red ball in first box, blue in second, red in first, blue in third, blue in first, red in second, red in second, blue in third, blue in first, red in third, and similarly blue in second, red in third. So these are the six possible ways. We can say that when distinguishable objects are distributed into separate subsystems, there are more possible ways for doing as compared to indistinguishable objects. So if you take distinguishable objects, we have more possible ways for doing the work as compared to if indistinguishable objects are there. Now coming to another example, calculate the number of ways in which the three balls of different color, that means distinguishable balls are there, can be distributed among four identical boxes without any restriction. So here, so the total number of possible ways are there. So the total number of possible ways are, let us, we will take the three, so let us, we will consider the three distinguishable balls, that is R, B and G. R for red, B for blue and G for green. And the ball R can be placed any of the four boxes of each of the, and the ball B can be placed any of the four boxes. Thus, there are 4 into 4, 16 ways of replacing R and B balls. And again, for each of these, there will be 4 replacing for G balls, and hence there are total number of ways 64, and hence there will be total 64 number of ways to arrange the three distinguishable balls among four identical boxes. Now coming to the next part, calculate the number of ways if you put a condition that box 1 can only have one ball and box 2 can have two balls. So here one restriction is there. Box 1 can have only one ball and box 2 can have two balls, where the third and fourth boxes have no balls at all. So in this way we can calculate. So the box 1, we have to put one ball in box 1 and two balls in box 2. 3 and 4 boxes will be remain empty. So there will be three different ways. Now, if we take a general consideration, in general, when n distinguishable objects are distributed in k boxes such that n1, n2, n3 and nk objects respectively, then according to the combinatorial mathematics, the number of ways W can be written as W equals to n factorial divided by n1 factorial into n2 factorial into n3 factorial up to and dot dot nk factorial. So in the present case means in this particular example, n equals to 3, total number of balls, n1 equals to 1, n2 equals to 2, n3 is 0 and n4 is 0, because for this example, so here it is given that box third and fourth box will be remain empty, so n3 will be 0 and n4 will be 0, and hence W equals to 3 factorial divided by 1 factorial. N1 factorial means 1 factorial, n1 factorial means 1 factorial, and then n2 factorial means, this is n2 means 2 factorial, then n3 factorial means 0 factorial, n4 factorial means 0 factorial, and the value will be 3. So for the result to get B, so 3 different values are possible. Now coming to one approximation, that is called Stirling approximation. This Stirling approximation is very important approximation, and that is also one type of long question. So that is also applicable to solid state chemistry, and that is also applicable to statistical thermodynamics. So the Stirling approximation, so the factorial number n is defined as, we know that n factorial means n factorial equals to 1 into 2 into 3 into 4 into up to dot dot into n. So that is n factorial equals to, if we so write in the reverse way, n factorial equals to n whole into n minus 1 into n minus 2 into n minus 3 up to dot dot 3 into 2 into 1. So this is just n factorial. And if we'll take logarithm of the above expression, so here this is equation 3.12. Here we have just written the n factorial. Now if we take the natural logarithm of this above expression, in the LHS side you will write ln n factorial. In the RHS side you have to write ln n into n minus 1 into n minus 2 into n minus 3 up to dot dot 3 into 2 into 1. And we know that ln A into B equals to ln A plus ln B. So the right hand side of this expression can be written as ln n plus ln n minus 1 plus ln n minus 2 plus ln n minus 3 plus dot dot ln 3 plus ln 2 plus ln 1. We can write the expression as the summation of the terms of the right hand side, and hence ln n factorial is equals to summation of ln n from 1 to n. Since n is a very large number, the summation can be replaced by integration. So here the n is a large number, so without using summation we can use integration. And here for integration we will put the limit n ranges from 1 to n. So the RHS of this expression can be replaced as integration. So that is integration of 1 to n ln n dn. So that is equals to ln n dn. So ln just if we take the integration of ln x dx, the value will be x ln x minus x. And similar way the value can be written as n ln n minus n, and here the limit is starting from 1 to n. And if we write the limit and expansion and expand the expression, we can write, so the value will be, if we put the limit, the value will be n ln n minus n minus 1 ln 1 minus 1. And again we know that, so the value will be, so this will become 0, 1 ln n minus 1, that will become 0, and hence the final result will be n ln n minus n. So this result gives the value of the Stirling's approximation. Now according to Stirling's approximation, ln n factorial equals to n ln n minus n. ln x factorial equals to x ln n x ln x minus x. So this is one long question and derivation of Stirling's approximation. And if we apply the Stirling's approximation for different numbers, the result will be like this. So if we'll apply the Stirling approximations by taking different examples. Suppose n equals to 5. Now applying Stirling's approximation, ln n, so if n equals to 5, then ln n factorial will be 4.79, and that means ln 5 factorial will be 4.79. But if we calculate the result using Stirling's approximation, because we know that according to Stirling's approximation, ln n factorial equals to n ln n minus n. ln n factorial equals to n ln n minus n. So this is the Stirling's approximation. Now, if you apply the Stilling's approximation for if the value of n equals to 5, we can write the LHS as 4.79, but we will get the RHS at 3.47. So here the percentage of error is 27.56. And if we will increase the value 10, that means if we increase the value of n as 10, so the LHS will be ln n factorial, that is 15.1, and the RHS will be n ln n minus n, that is 13.03. Here the percentage of error is 13.71. And if we will again take another value of n, that is suppose that is increased to 100, so here ln n factorial is 363.74 ln. So this represent the LHS of Stilling's approximation, and if you use the RHS of the Stilling's approximation, the value will be 360.52. Here the percentage of error again decreases. So that means if the number will increase, the percentage of error will gradually decrease, and if the number is around 1 lakh, then the percentage of error is 0.00061. So hence it is very important that Stilling's approximation gives good result for a very large values of n. However, for smaller values of n, the result does not match the actual value. So the Stilling's approximation will be applied if large number of atoms are there, large number of molecules are there, large number of ions are there. Particularly, the Stilling's approximation will be applied in the solid, in the ionic solid to calculate the number of Schottky defect and number of Frenkel defect, because we know that in ionic solid the number of Schottky defect and number of Frenkel defect are excessively large, because it will take 1 mole of the solid is made up of 1 mole of cation and 1 mole of anion, that is 6.022 into 10 to the power 23. So this Stilling's approximation will be applied for very large, if very large number of objects will be there. But the Stilling's approximation will not holds good for lesser number of objects. If less number of objects will be there, we cannot apply Stilling's approximation. Generally, in chemistry, we are applying Stilling's approximation when excess number of atoms or excess number of ions, or if the number will be very large. Because we know that in chemistry, 1 mole means 6.022 into 10 to the power 23 numbers. For such numbers, the Stilling's approximation will give accurate result. Now coming to the next one is probability distribution function. So when an experiment is carried out and there are different possible outcomes, so if we carried out one experiment and different possible outcomes are there, when an experiment is carried out, there are different possible outcomes. Each outcome has some probability of occurrence. To characterize a random variable, we first need to uh, uh, here just for 2 3 minutes. I will start after 2 3 minutes. Okay. So now we will start from probability distribution function. So when an experiment is carried out and there are different possible outcomes, and each outcome has some probability to occurrence. To characterize a random variable, we need the information of all possible outcomes of the elementary event and of the random variables, then get the probability to give the value of the possible outcome. So we will discuss one example here. And again, so remember that in case of tossing a coin twice, there are four possibility outcomes. There are four possible outcomes, and we could calculate the probability of getting a particular outcome. That is called probability distribution, that refers to variation of probability of occurrence of all possible outcome in an experiment. So here we will find out the probability distribution means the probability distribution means variation of probability of occurrence of particular result or particular outcome from one set of experiment. So each outcome has its own probability of occurrence. However, the total probability of occurrence of all the event always one. So if you consider the total probability, so if you add the total probability, that will become one. Now let us recall the experiment given in the above, in which two dice are rolled simultaneously. The minimum value of sum of the numbers on the top face of the two dice will be 1 plus 1, 2, and the maximum value will be 6 plus 2, 6, that is 12. And the other possible sums are 3, 4, 5, 6, 7, 8, 9, 10, and 11. And here the number of permutations and the probabilities of different outcomes rolling of two dice. So rolling of two dice. Here the permutations are the two dice may be 1 and 1, and the sum of the result is 2, and the number of permutation is 1. And total number of possibilities is 36. So its probability is 1 divided by 36, that is 0.028. And to get the summation 3, the permutations are first will be 2 and second will be 1, or first will be 1 and second will be 2. So there will be two permutations are there, and the number of permutations will be 2, and hence the probability will be 2 by 36. And if you want the summation of the result should be 4, then the number of permutations will be 3, 2 and 2, 1 and 3, 3 and 1. So here the number of permutation will be 3, and the probability will be 3 by 36, that is 0.083. And here you should know that the probability of getting the sum value of the two dice will be 7, will be maximum, that is 6 by 36, that is 0.163. So in this case the possible outcomes for the two dice are 6. 6 each are independent of each other. Then according to the fundamental counting principle, the total number of possible outcomes, that is the number of permutations, is 6 square, that is 36, because two dice are there. So the total number of permutations should be 6 square, that is 36. And the last column of the table gives the probability of each possible set of the probability of each possible set of permutation from the sum of the numbers on the top faces of the dice. You can clearly see that the probability depends upon the outcome. If we plot a graph taking probability versus outcome, that is known as probability distribution curve. So if we plot a graph here, so this is the y-axis to represent the probability, and the x-axis represent the sum of the two results obtained from the two dice. So the probability to getting the sum 7 is maximum, and this type of curve is called probability distribution curve. Now since the outcomes in this experiment have discrete values, the probability distribution function is called discrete probability distribution function become the result have discrete values. There is no fractional values or no continuous values will be there. The result have discrete values of probability of distribution function, and hence that is called discrete probability distribution function. In such a case, the total number of possible arrangement can be obtained by adding the values represented by the bars in the histogram, and mathematically that will be probability px1 plus px2 plus px3, that is equals to summation of pxi from I from 1 to n, and the probability of the variable having the given value f1 of the sample is defined as, so if you want to find a particular result, the probability will be f1 divided by summation of I to n fi, and the average of the function is equals to sum of the values of the function of all the values xi multiplied by the probability of the variable with the corresponding value. So this is the probability of so the distribution of function f of x equals to summation of f of xi into p xi starting from n starting from 1 to n. However, when the number of possibilities increases, it becomes increasingly difficult and the time consuming process to count the possible number of permutations, because in chemistry generally we are considering very large number of atoms or molecules. So in this case it will be difficult to find the result by using this table or counting the numbers, and hence uh, for large number of samples or large number of atoms, molecules, etc., we have to use the formula. In such cases where the possible outcomes do not form discrete set of continuum in R, and the distribution of probability can be expressed by a smooth function that is called continuous probability distribution function. And here we will discuss the probability density, and the total number of possible arrangement in such cases equals to area under the given curve. This can be determined by suitably integrating the probability function, uh, and in probability density function the probability of an outcome is a small range of outcome and dx is given. So for a very small number of so if you consider a very small number of outcome, in that case the differential term dx will be there, and if you add the total number of results, then we will take the integral function. So this is the integration of px dx from x1 to x2, and the probability distributions are usually normalized. It implies that it will satisfy the following criteria. So this is the criteria for normalization: the total integral value. If the total integral value will be 1, that is called normalization criteria. And the probability of a variable having the given value f of x in the range of x is defined as px dx equals to f of x dx divided by integration of f of x dx from x1 to x2. And here, the probability that can be used to determine average values of some variables. Let us consider variable x that can have certain possible individual values xi. If we represent the probability that a given value xi exists as pi, then the average value of the x can be given as x bar equals to summation of xi pi from 1 to n divided by summation of pi. So here we'll now we'll move to, so in this unit we have discussed about the basic mathematical tools to calculate the probability distribution functions and probability of getting certain results, and this principle will apply in thermodynamics to calculate the results in the next unit. So in the next unit we will discuss about the Boltzmann's distribution in a system containing many molecules. Suppose Avogadro's number of molecules, the available quantized energy states are occupied by different fraction of molecules. So as we are discussing the atomic and molecular levels, and in atomic or molecular levels, the quantization of energy states, the atoms are or molecules are available in quantized energy states. So this is the entire population of molecules is distributed among the different energy states. So population means the number of atoms or number of molecules present in a particular energy state, so that is known as population. And the entire population of molecules is distributed among the different energy states. And alternatively, we can say that the total energy of the system is distributed among the constituent molecules. And here Boltzmann was the first person to propose an expression to calculate the population of different energy states, and this expression is known as Boltzmann distribution function, and that is essentially a probability distribution function that will allow to calculate the probability of finding the system in a certain energy states. So in this Boltzmann distribution function, we can find we can easily find the we can easily calculate the probability of finding the system in a particular energy state. Now, before discussing the Boltzmann distribution, first we will discuss the microstates and configurations. So that means in this unit, we will apply the same previous principles for atomic or molecular level. Now let us consider a simple molecular system containing three quantum particles. Quantum particles means very small particles are comparable to atoms and molecules. So here we are containing the so if we consider a simple system or simple molecular system that containing three quantum particles that collectively have an energy equals to three quanta. So the three quantum particles have energy 3 quanta. That means each particle having energy 1 quanta. So the energy states available for the particles having energies 0 energy state, epsilon 0 energy state, 2 epsilon 0 energy states, 3 epsilon 0 energy states, and so on. Where epsilon 0 represent a quantum of energy. Now the question, what is the most probable distribution of energy? So here, and what is the most likely way? The most likely way in which the total energy three quanta. So here epsilon 0 state having the energy 1 quanta, epsilon 2 epsilon 0 state having the energy 2 quanta, 3 epsilon 0 state having the energy 3 quanta, and 0 state having the energy 0. And here we have to distribute the three particles, the three quantum particles in different energy states, and hence after that we should get the total energy of the three molecules or the three particles should be three quanta. To begin with, we assume that the particles are indistinguishable and try to work out the possible distribution. So here we will first consider that all the three particles are same kind, and hence we cannot distinguish. All the three particles are same kind, and the total energy should be 3 quanta. Three quantum particles are there, three particles are there. The total energy should be 3 quanta. We have to arrange the three particles in three different energy levels. If the particle will present at epsilon 0, its energy will be 1 quanta. If the particle will present at 2 epsilon 0, its energy will be 2 quanta. If the particle will present in 3 epsilon 0 energy level, its energy will be 3 quanta. So there are three possible ways as shown in the figure. In the first case, all the three molecules are present in epsilon 0 state. So if all the three molecules are present in epsilon 0 state, for the first molecule the energy is 1 quanta. Similarly for second molecule it is 1 quanta. Similarly for third molecule it is 1 quanta. So for all the three molecules the total energy will be 3 quanta. So this is one possible way. And in the second possible way, the first molecule should be present on zero level, having zero energy. The second molecule should be present on epsilon zero, having one quanta of energy. The third molecule should be present in 2 epsilon zero, having 2 quanta of energy. So in this case, the total energy of the three molecules is also 3 quanta. And the third possibility is there, the two particles should be present on a zero level, having zero energy, and the third molecule should be present in 3 epsilon 0, having 3 quanta of energy. So all the three possibilities you can show, you can see the total energy of the three particles will be 3 quanta. Here 1 quanta, 1 plus 1 quanta plus 1 quanta plus 1 quanta, that is equals to 3 quanta. Here 0 plus 1 quanta plus 1 quanta, that is here 0 plus 1 quanta plus 2 quanta, that is equal to 3 quanta, and here 0 plus 0 plus 3 quanta equals to 3 quanta. So the three possible configurations for distributing 3 quanta of energy among the three particles. And here we have we assume that the three particles are indistinguishable. Thus, we see in the above example, there are three different ways for arranging the three particles or three molecules in various energy states such that the total energy of the system is 3 epsilon 0, that is 3 quanta. Such arrangement of molecules in different energy states are called configurations. You may note that we have assumed that all the molecules are indistinguishable. But if we will take three distinguishable molecules, then the number of possibility will be increased. So in the next example, consider a system containing 5 indistinguishable particles, that is n equals to 5, which can occupy any of the available energy levels having energy equals to epsilon 0, 2 epsilon 0, 3 epsilon 0, 4 epsilon 0, 5 epsilon 0. And if the total energy of the system is 10 epsilon 0, identify the different possible ways which give in which the molecules can occupy various energy states. So this is the figure you can see in the figure. So this is the 6 possible ways, so that the total energy of the system should be 10 epsilon 0. So in the first way, all the 5 molecules will be present at energy level 2 epsilon 0. So the total energy of the system will become 10 epsilon 0. And for the second possibility, the first molecule will present at epsilon 0, then 3 molecules will present at 2 epsilon 0. So the total and the the fifth molecule will present in 3 epsilon 0. So in the second possibility, also the total energy of the system will become 10 epsilon 0. Similarly, in the third possibility, two molecules present at epsilon 0, two molecules present at 2 epsilon 0, and one molecule will present at 4 epsilon 0. And in the fourth possibility is that two molecules will present in epsilon 0, one molecule will present at 2 epsilon 0, two molecules will present at 3 epsilon 0. So 3 plus 3 6 plus 2 8 plus 1 plus 1, that will become 10 epsilon 0. And in the fifth possibility, you can see three molecules will present on epsilon 0 energy level, one molecule will present on 2 epsilon 0 energy level, and one molecule will present on 5 epsilon 0 energy level. So the total energy of the system will become 10 epsilon 0. So these are the 6 possible ways to getting the total energy of the system 10 epsilon 0. Now see what happens if the molecules are, so in this case all the 5 molecules are indistinguishable. But if we'll consider all the 5 molecules are distinguishable, that means all the 5 molecules are different. When distinguishable objects are distributed into separate subsystems, there are more possible ways for doing so as compared to that of the indistinguishable object. Because a similar type of examples we have discussed in the previous unit, In the first case, we have taken three molecules, red color, three balls of red color, and in the second case, we have discussed three balls of different color. One is red color, one is blue color, and one is green color. So, if distinguishable molecules are there, then the number of possibilities will be increased. So, in such case, each configuration can have one or more than one permutation possible. Let us consider the example of distribution of three quanta of energy among the three quantum particles discussed above. So that means here we will take the example of this example when the three molecules are distinguishable. We take these particles are distinguishable. We find that three configurations are identical for each of the distinguishable particles. So if the three molecules are distinguishable, then the number of possibilities. So here so this is configuration one, in which the three molecules present in epsilon 0, and here this is configuration 2, in which one molecule will present in 0 energy level, one will present in epsilon 0 energy level, and one is present in 2 epsilon 0 energy level. And in the second, so here the total energy will become 3 epsilon 0. And in the second case, one molecule will present in 0 level, one will present in epsilon 0, and one will present in 2 epsilon 0. Here also the total energy will become 3 epsilon 0. So why this number of possibilities will increase? Because here the three molecules are distinguishable. One is red color molecule, and another one is green color, and another one is blue color. So in the first case, the red color molecule present on 0 energy level, the green color molecule present in epsilon energy level, the blue color molecule present in 2 epsilon energy level. And in the second case, only the color of the molecule will change. That means the first molecule present in 0 energy level, the second molecule, that means green molecule, will present in 2 epsilon 0, blue present in epsilon 0. Here also the total energy of the system will become 3 epsilon 0. And similarly, six possibilities are there for this type of configuration. This type of configuration means one molecule will present at 0 energy level, one will present at epsilon 0, and one will present at 2 epsilon 0. So for these six possibilities are there. And in configuration 3, two molecules will present at 0 level, one molecule will present at 3 epsilon 0. So the total molecule will become 3 epsilon 0. So in this case, three possibilities are there. So this is the configuration and the corresponding microstates for the distribution of three quanta of energy among the three distinguishable particles. So here we have observed that when the particles are distinguishable, the number of possibilities are increased. Now, if we consider a generalized term, a configuration in this case is represented as N0, N1, N2, N3, where N0, N1, N2, N3 refers to the number of particles in the energy states 0, epsilon 0, 2 epsilon 0, and 3 epsilon 0 respectively. So, there is three configurations given above as represented as 0300, 1110, 2001 respectively. It is important to note that the total energy of the arrangement is same, and the only difference is that the distribution of the energy over the particle. So the total number of microstates associated with a given configuration is known as weight of the configuration, and that is represented as W. Now a question comes up that which of the possible configuration is likely to be observed for the system of equilibrium, since all the microstates have an equal priori probability of being observed. So the probability of observing the 1110 configuration is maximum number of microstates having W equals to 6. So here, so this is the probability. So the probability to observe 1 1. So the probability to observe 1110 configuration which have maximum number of microstates, that is 6, will be maximum in this case, and hence the probability of observing this configuration is simply the number of microstates associated with the configuration divided by total number of microstates possible. And here for all the configuration put together, that is 6 by 10, that is equals to 0.6. So the three particles case discussed above provides a general approach to determine the most probable configuration of energy in the chemical system. That is, we work out all the possible configuration of energies and determine the corresponding microstates. The configuration with greater number of microstates is likely configuration. Is the likely configuration. That means the configuration in which will produce greater number of microstates. Microstates means degenerate energy levels. So the configuration where greater number of microstates will be there, that is the likely configuration of distribution of different molecules for a particular system. Such an approach in which Such an approach is fine for the system with smaller number of particles. So here we are considering smaller number of particles, and hence we can easily find out that. However, it is difficult task to do similar exercise for a practical chemical system having astronomical number of particles, because if you apply this principle for a practical chemical system, then large number of molecules or large number of particles are there. For example, if you take 2 moles of particles, that means 2 into 6.022 into 10 to the power 23 particles were there. So for for such a large number of particles, to find this type of result is very difficult. So for such a case, we need to find a way to obtain the number of all the microstates associated with a configuration without any counting. That means we cannot count if we consider this principle for a particular chemical system. For a chemical system, it is very difficult, or it is impossible to count the number of microstates. And fortunately, it is possible to work out an expression for the same. But that type of expression can be calculated using a generalized formula. So the problem in hand is to work out the number of possible ways of distributing n distinguishable particles among different energy levels epsilon 0, epsilon 1 and epsilon 2 dot dot r. N0, suppose total number of distinguishable particles will be, suppose total number of distinguishable particle will be n. N is the total number of distinguishable particles, and the different energy levels are epsilon 0, epsilon 1, epsilon 2, etc. And there are n0 number of particles present at epsilon 0 energy level, n1 number of particles present at epsilon 1 energy level, n2 number of particles present at epsilon 2 energy levels, and n3 number of particles present at epsilon 3 energy levels, and so on. So in this case, to begin with, we assume that a given energy state can be had only one single particle. So in order to find the formula, here we will consider for a given energy state that will have only one single particle. Now, since there is a total number of n particle, we can assign an energy state of the first particle in n different ways. Suppose we will suppose n number of particles are there. Out of the n number of particles, we have to choose a single particle and distribute the single particle in different energy level. So we can assign an energy state to the first particle in n different ways, because total n different number of energy states are there. So for first particle, we can assign n for the first particle can be assigned into n different ways, because n different energy levels are there, total n number of particles are there. But for but out of the n number of particles, if we consider the first particle, we have to arrange the first particle in n different ways. And similarly for second particle, after arranging the first particle, for the second particle the number of ways will become n minus 1. And similarly for third particle, the number of ways to arrange will become n minus 2. And similarly that will become again n minus 3, n minus 4, dot dot 3, dot dot 3 into 2 into 1, that is n factorial ways of assigning the energy states of n distinguishable particle. So if n distinguishable particles are there, we have to arrange the n distinguishable particles in n number of energy states. So the possible ways of arrangement will be n factorial. Now you recall for your earlier classes that in a chemical system of all the particles do not have same energy, and a given energy can be expressed by many particles. So if n number of particles are there, all the particles do not have same energy. For a out of the n number of particles, for a particular set of particle having same energy, but all number of particles do not have same energy. So in this, for this, we can solve this type of problem using Maxwell distribution of molecular velocity. And the Maxwell distribution of molecular velocity we have studied in the for gaseous for in the gaseous state. It implies that more than one molecule can have same energy level. So if out of the n distinguishable particles, so these are so assigned that the different states that have n0 states, n0 number of particles present in epsilon 0 energy state, n1 number of particles present in epsilon 1 energy state, n2 number of particles present in epsilon 2 energy state, and so on. Thus, by considering thus, by considering that a given energy state can be had only by a single particle, we have overestimated the possible microstates, and we need to make a necessary change by correcting the overcounting identical permutations. So now, since each of the n0 particle can have energy equals to epsilon 0, so there are n0 factorial different ways in which the distinguishable particle could have been selected to have energy states epsilon 0. And similarly, n1 particles could have assigned epsilon 1 energy state in epsilon 1 factorial and so on. Therefore, the total number of distinguishable ways for distributing n number of particles to the different energy states are required, and for this, the order in which the particles were chosen, so that is weight of the configuration is W equals to n factorial divided by n0 factorial into n1 factorial into n2 factorial into n3 factorial dot dot. So if we'll apply this weight factor W, the value of W in the three particle system, that is n equals to 3, we can calculate the number of microstates of different configurations. So here for n equals to, so this is for configuration, first configuration. In the first configuration, all the three particles are present at n1 level having epsilon 1 energy. So the total energy of the system will become 3 epsilon 0 or 3 quanta. So the number of permutations is 3 factorial divided by 3 factorial. And the probability is 1 by 10, that is 0.1. And in the second state, 1, 1, 1. So the number of particles in different energy levels. In the first n0 energy level 1 particle, n1 energy level 1 particle, and n2 energy level 1 particle. And for n0 energy level, the energy of the system is 0. For n1 energy level, the energy of the system is 1 quanta. For n2 energy level, the energy of the system is 2 quanta. So the total energy will become 3 quanta, and the number of permutations will be 3 factorial divided by 1 factorial into 1 factorial into 1 factorial. Here, if you apply this W value, this equation to the previous example, so here that will become total 3 factorial divided by 1 factorial into 1 factorial into 1 factorial. So 6 possible ways are there what we have calculated in the previous example. Exactly same value will come, and the probability will be 6 by 10, that is 0.6. And similarly for the third configuration, two molecules are present in N0 energy level having zero energy. One molecule will molecule will present in epsilon 1 energy level, and one molecule will present in epsilon 2 energy level. So in this case, uh, the total energy of the system will become 3 quanta, and the permutation or weight or the number of weight will become 3 factorial divided by 2 factorial into 1 factorial, that is equals to 3, and the probability will be 3 divided by 10, 0.3. So for first configuration, the probability is 0.1. For second configuration, the probability is 0.6, having highest probability. For third configuration, the probability is 0.3, and the total, if you add the total probability, that will become 1. Now the probability of observing ith, so the same principle, if we generalize this principle, the probability of observing ith configuration is given by the weight of ith configuration divided by the total weight of all the configuration put together. So the probability for getting ith configuration Pi equals to Wi divided by W1 plus W2 plus W3 plus dot dot Wn, and which is equals to Wi divided by summation of Wi1 to n. So here the number of permutations of microstates of each configuration for a system containing 5 particles with total energy equals to 10 quanta or 10 epsilon 0. So so we will apply this equation to that particular example. So here in the configuration 1, all the molecules will present in epsilon 1, and the epsilon 0, all the molecules will present in epsilon 0, that is the second energy state. And here the number of, and if the particles are distinguishable, so the number of different energy states n2 equals to 5, and the permutation will be 5 factorial by 5 factorial, that is equals to 1. So this is the number of permutations, and hence the probability will be 1 by 121, that is 0.008. In the second configuration, you will find 1 3 1. So that means, so this is the distribution of 5 molecules in different energy levels, and here n1 equals to 1, n2 equals to 3, and n3 equals to 1. And the number of permutations will become 5 factorial by 1 factorial into 3 factorial into 1 factorial, that is equals to 20 divided by 121, that is equal to 0.165. Similarly, for the third configuration, that will become 2 1 2, n2 equals to 2, n1 equals to 2, n2 equals to 1, and n3 equals to 2. And the number of permutations or number of weights equals to 5 factorial by 2 factorial into 2 factorial, that is equals to 30, and the probability will become 0.248. Similarly, for next configuration, the two molecules will present in first energy level, two molecules will present in second energy level, and one molecule will present on fourth energy level. So the total energy of the system should be 10 epsilon 0 or 10 quanta. Now here in this case, n1 equals to 2, n2 equals to 2, and n4 equals to 1, and the number of permutations will become 5 factorial divided by 2 factorial and 2 factorial. So the probability will also same. And this is the fifth configuration. In the fifth configuration, 3 molecules present in first energy level, one will present in second energy level, and one will present in fifth energy level. So n1 equals to 3, n2 equals to 1, and n5 equals to 1. The total weight will become 5 factorial by 1 factorial into 3 factorial into 1 factorial, and that is 20. Similarly, for the last sixth state, uh, 3 molecules are present in the first energy level, one molecule will present in second, and one molecule will present in fourth. That is n1 equals to 3, n3 equals to 1, and n4 equals to 1. So the total weight will be 20 and the probability will be this. Now if you add all the probability, so that will give rise to 1. So these are the 6 different configurations, and where the if you add all and the corresponding probabilities are there, 6 different configurations. So such that 6 different configuration in which the total energy of all the 5 molecules should be 10 epsilon 0, and the corresponding probabilities are here. If you add all the probabilities, so that will become 1. So you will recall from the previous unit that such a distribution is dictated by the probability, and most likely distribution will correspond to a configuration in which highest number is associated highest number of associated permutations. Therefore, in the current example, the configuration 3 and 4 are more likely. So that means if we consider a set of 5 molecules, so that the total energy of the system will become 10 epsilon 0, and the arrange the 5 and 4 sorry the 3 and 4, the third and fourth arrangement will be the most likely occur arrangement, because its probability will be more. So these two arrangements are the more possible arrangement, because here here it has high probability, that is 0.248 among the 6. Therefore, in the current example, the configuration 3 and 4 are most likely, that is, these are dominant configuration. In other words, the configuration have the maximum weight is the dominant configuration. Now we'll take another example. In the another example, consider a system containing 5 molecules which can occupy any of the available energy states, having energies equals to 0, epsilon, epsilon, 2 epsilon, 3 epsilon, 4 epsilon, 5 epsilon. So we will consider 5 molecules, and the 5 molecules can occupy any of the available energy states. So the available energy states are 0, epsilon, 2 epsilon, 3 epsilon, 4 epsilon, and 5 epsilon. But the condition is that if the total energy of the system should be 5 epsilon, calculate the different possible ways in which the molecules can occupy the various energy levels. So in this example, we can apply, so this is the distribution, total distribution we have calculated, but we can apply the formula to find out the possible energy states. And in the second part, it is given repeat the experiment with 50, 500, and 1000 molecules to be distributed among the same energy levels, with total energy still being 5 epsilon. So that means if you take 50 molecules, 500 molecules, and 1000 molecules, and arrange in these 6 energy levels, so that the total energy of the system will become 5 epsilon. So here in the coming to the second part, in the second part, so these are the possible distribution and configuration weights and probabilities of 50 molecule under the same set of conditions, so that total energy of the molecules will become 5 epsilon 0. So in this distribution, in the distribution 1, 49 molecules will present in 0th energy level, and 1 molecule will present in 5th energy level, so that the total energy will become 5 epsilon. Here the weight will be 50. And in the second case, 48 molecule will present in 0 energy level, 1 molecule will present in epsilon energy level, and 1 molecule will present in 4 epsilon energy level. So the total energy of the system will become epsilon plus 4 epsilon. Here W value will be 2450. So you will check the value of the W. And so these are the different possibilities. So in the seventh possibilities, 45 molecule will present in 0 energy level, and 5 molecule will present in epsilon energy level, so that the total energy of the system will become 5 epsilon. Here the W value will become very high. So if we will add all the probabilities, so that will give rise to 1. Hence the configuration number 7 is the dominant configuration. So here seventh configuration is the dominant configuration having highest probability, and here the probability is 0.67. And similarly, in the second, the possible distribution and the corresponding weight of the probabilities of the 500 molecules. So here we have calculated for 50 molecule, but if you calculate for 500 molecules, so you will find that for 500 molecule, the seventh distribution is having highest probability, 0.9608. Here the probability is the highest probability. So in the seventh probability, 495 molecules will present in zeroth energy level, and only 5 molecules will present in epsilon energy level. So the total energy of the system will become 5 epsilon. And similarly, if we arrange 1000 molecules, its probability of the seventh configuration will still increase. So coming to the comet part, on the basis of the calculation given above, we note that as the number of molecules increase, the weight of the more probable configuration or the probability of the dominant configuration also increase. So if we increase the number of molecules, the probability of the dominant configuration also increase. Okay, so the remaining part we will discuss tomorrow. Okay.
Okay, sir. Thank you.
Okay, sir. Thank you.